did you accidentally take it home?
All right.
Because he's using my locker, so I grabbed it with my locker.
We'll worry about that later. Let's worry about the lecture now. Okay. So today's lecture, one of the easiest in the book, but also one of the material we're covering today is one that's ubiquitous in math. This doesn't just apply to discrete math. This is going to be techniques that you use no matter what field of math you're in. And what we're doing today is we're focusing on mostly proof by contradiction. So thus far, what has a proof been in all your proofs? All your proofs have been of the form alpha implies beta. If some statement alpha, if alpha, then beta, right? Everything you proved could be reworded this way. And then what was the first line of your proof always? Let alpha, whatever alpha is. Let alpha, dot, 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 therefore beta. Whatever the statement alpha and beta were. And that's roughly what your proofs have looked like this whole time, right? And that's what we call a direct proof. When you just show directly that alpha implies beta. Now, we already learned about the contrapositive. The contrapositive, so the way you're used to proving is alpha implies beta, you assume alpha, show that implies beta. The first thing we're going to talk about is the contrapositive. The contrapositive of alpha implies beta is not beta implies not alpha. We've already talked about this a little bit. And these are logically equivalent statements. We'll show it with the truth table, but first let's get the intuition for it. If this is a statement, if Donnie's wearing shoes, then Donnie's wearing socks, is logically equivalent to, if Donnie's not wearing socks, then Donnie's not wearing shoes. Make sense? So they're logically equivalent statements. And we can also do our proofs thinking about it this way. This is another way of thinking about alpha implies beta. It's logically equivalent to alpha implies beta, which means we can prove this way. We can start out our proofs with 1, let, not beta. And we can go dot, 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 and show, therefore, not alpha. And that's logically equivalent. And sometimes it's easier to think about it that way. And so that's proving with the contrapositive. So let's really quick show that those are logically equivalent, and then go through an example of proving with the contrapositive. So truth table really quick. Back to what we know and love, alpha and beta here. What are all the possible combinations?
True, false.
I can have true, true. I can have false, false.
What? Okay, that works. True, false, false, true.
True, false, false, true. Okay, those are all our 4 possible combinations of alpha and beta. Now, here we'll put not alpha, then I'm just going to negate this column, right?
False, true, true.
Perfect. This, we just negate beta.
False, true, false.
And then finally, see if you guys have regressed. Now we're going to do alpha implies beta.
True.
True implies true is?
True.
True. False implies false is?
True.
False implies false is?
True.
True. It's vacuously true. Anytime the antecedent is false, the implication is true. All right. True implies false is?
False.
That's the one that's false. And then false implies true is false.
True.
Oh, true. Okay. Vacuously true. All right. So now let's do the contrapositive. So the contrapositive is not beta, it implies not alpha. So false implies false is?
True.
What? False implies false is?
True.
Oh, okay. True implies true is?
True.
True implies false is?
False.
False. True implies false is false.
Right.
If I'm wearing shoes, I'm president of the world. True antecedent, false conclusion. Is the whole implication true? No, the whole implication is false. All right. And finally, false implies true is?
True.
True. If I'm a purple dragon, then I'm president of the world. That's true.
Yep.
All right. We'll come back to this one, but let's just do a proof now using contrapositive to see it in action. So let R be an equivalence relation. What's an equivalence relation?
It's symmetric, transitive, and reflexive.
It's a relation that's symmetric, transitive, and reflexive. What does it mean for a relation to be reflexive?
X equals X.
No. X is related to X.
Yeah, it's related to X.
For every x in the set, every element in the set is related to itself. This is going to be on the test, so I hope you guys are following that. You better know those 5 relation properties. The whole test is almost just those.
Really?
There's 5.
Anti-symmetric.
Reflexive, symmetric, transitive, irreflexive, antisymmetric.
Irreflexive.
It's just irreflexive.
So it's just not reflexive.
No, not reflexive and irreflexive are very different things, and we hammered this home when we went over it.
We went over
X
this
is
too.
not related to X.
Irreflexive is x is never related to x. Reflexive is x is always related to x. If it's sometimes related and sometimes not, then it's neither of us. All right, so let R be an equivalence relation on some set A, and let little a and little b be elements in some set A. What are we trying to prove? I'm trying to prove that if A is not related to B, then, what is that a symbol for?
Equivalence class.
A's equivalence class, perfect. So if A is not related to B, then A's equivalence class intersected with B's equivalence class equals the empty set. Or in other words, if A and B are not related, their equivalence classes have no elements in common. Their intersection is empty means that they have no elements in common. They don't overlap at all. You with me?
Mm-hmm.
So we're trying to show that alpha implies beta. Now, if I were to start to prove this, you might get kind of stuck. If we started with, assume that A and B are elements of a set such that they're not related, now I need to show that their equivalence class's intersection is the empty set. I don't really know a good way to use that information. What does it mean for A and B to not be related?
They're not.
There's not like a good definition for that.
Yeah.
There's a good definition for if they're related, I know what that means and I can start playing with it. But I don't really know how to unravel this definition. So when you go and you first write something like that and you get kind of stuck, and you think, I don't really know, like there's not a definition of the not of this thing, then it's common to think, can I prove this by contrapositive? So rather than showing A is not related to B implies that their intersection is empty, I'm going to show not this implies not this. Right?
Right.
Here's my alpha, here's my beta. Rather than showing alpha implies beta, I'm going to show not beta implies not alpha. You with me?
Yeah.
Mm-hmm.
So assume not beta. Assume that their intersection is not empty. And I'm going to show that it implies that they are related. Make sense?
Mm-hmm.
Okay. And I know how to use the fact that their intersection is not empty. That's easy. So the rest of this proof almost follows for free. It's the first step to think about using the contrapositive that I think you'd mostly get stuck on. So once you realize to use contrapositive, okay, then we're pretty well off. So assume that A and B's intersection is not the empty set. What does it mean for the intersection to not be the empty set?
Means that
They're related.
It means that they have something in common. If two sets' intersection isn't empty, then there's something in their intersection. So since their intersection is not empty, then that means that there must exist some x in their intersection. There must be something in their intersection. Right? And if there's something in the intersection of those sets, that thing must be in the first set and in the second set.
Yeah.
And now I know exactly what it means for x to be in A's equivalence class. That means x is related to A. And I know exactly what it means for x to be in B's equivalence class. That means x is related to B. So I now know x is related to A and x is related to B. I know R is an equivalence relation, so if x is related to A using symmetry, I also know A is related to x. So if x is related to A and x is related to B, I also know that A is related to x and x is related to B. Right? You see how I got from here to here? And then how did I get from here to here? Transitivity. Since R is transitive, then A being related to x and x being related to B implies A is related to B. Right? If Debbie's shorter than me and I'm shorter than Hayden, Debbie's shorter than Hayden. Transitive. Okay. So, therefore, we just already showed A is related to B. So notice what we showed. We showed not beta implied not alpha.
Yeah.
Therefore, if alpha is not related to beta, then their intersection must be empty. You ever follow the logic there?
Yeah.
We start with not beta, and we showed that implied not alpha. So we showed alpha implied beta.
Okay.
Good?
Yep.
Because those are logically equivalent. Okay. The next idea is a proof typically called, in more general context, a reductio ad absurdum proof. Fancy Latin for saying a proof. If I prove that some scenario implies an impossibility, then the scenario didn't happen. What's a common example? Let's say that you know that Phoenix was here yesterday, but you also thought you saw him on screen in the crowd at a football game. But you know it's impossible for Phoenix to be in two places at once. That would be absurd. Therefore, you can conclude, no, you did not see him on the screen at the football game. It implies something absurd. Okay? So that's the way we think about it. So rather than showing alpha implies beta, we say, assume alpha, and let's assume that beta is false. And we're going to show that that implies an impossible worldview. So if beta being false implies something impossible, then we know that beta must be true. Make sense? That's the way that these proofs often work. So you still assume alpha like you're used to. Assume alpha the same way we do in a direct proof. But then you say, let's assume that beta is false. You say, assume by way of contradiction beta is false. You show that implies something impossible, some statement that for sure is always false, and therefore beta couldn't have been false. And so beta has to be true. Make sense? The logic there? All right, so let's go over the truth table for it to see that these are actually logically equivalent, and then we'll do some proofs using this, because this is the harder way to think about proofs. Okay, let's look at it. Up here, what's alpha and not beta? True and false is?
True.
False.
False.
True and false is false. False implies false is
True.
true. So here we get a true. Okay? Let's look at the next one. False and true is?
False.
False implies false is?
True.
True. Let's look at the next one. True and true is?
True.
True. True implies false is? False. And then finally, false and false is? False. False implies false is? True. And so notice, surprise, surprise, logically equivalent to alpha implies beta. Okay? Alright, let's see this in action. If x is an integer, then x is not both even and odd. So what's my alpha going to be here?
X.
X is an integer. Alpha is x is an integer. Beta is
X is not both even and odd.
yes. Beta is x is not both even and odd. So what's the negation of beta? What's not beta?
It's even and is both even and odd.
X is both even and odd. So I'm going to show that x being an integer and x being both even and odd implies something false. That's what I'm going to show. And that's logically equivalent to showing alpha implies beta.
Okay.
Alright, so let's set this up. So if x is an integer, then x is not both even and odd. You warn your reader when you're going to do proof by contradiction, because the logic here is a little bit messier, and so let the reader know what you're going to do. So you start these proofs out with, assume by way of contradiction. So often that those four letters, you'll get used to them. Assume by way of contradiction that x is an integer, there's our alpha, and x is even and odd. There's not beta. Here's alpha, here's not beta. beta is not both even and odd. So not beta is both even and odd. Everyone see that this is alpha and beta, or alpha and not beta.
Yeah.
Perfect. So let x be an integer and assume that x is both even and odd. Well, since x is both even and odd, what does that mean by definition? Well, then there must exist integers a and b such that x is equal to a, x is equal to 2a, since x is even, and x is equal to 2b plus 1, since x is odd. Right?
Yeah.
Okay, perfect. Then, since 2a is equal to x and 2b plus 1 is equal to x, then 2a is equal to 2b plus 1.
Right.
With me? Okay. I'm going to move the 2b to the other side, so subtract 2b from both sides. Follow that?
Yeah.
Divide both sides by 2. Follow that?
Yep.
So now I've got a minus b is equal to 1/2. What is a?
An integer.
What is b? Can I ever get an integer minus an integer gives me a fraction? No, that is impossible. There's our big false statement. So, just trying to hit the point home, but you might have already seen it from here. Observe that a minus b equals 1/2, and that a minus b always has to be an integer. That's a contradiction, and that's what that back and forth arrow means there. That means we have just demonstrated a contradiction. I cannot have both the case that a minus b is equal to 1/2 and a minus b is an integer. That's impossible. That's as impossible gets. This whole statement right here, alpha minus beta equals 1/2 and a minus b is an integer, is a statement that always evaluates to false. There's our f right here. So I just barely showed a and not b implies a statement that's for sure 100% of the time, no question about it, false. So there's a big F. So then we put that symbol there when we've shown our big F to let the reader know. Hey, you should have just read your big F. Therefore, x is not both even and odd. Because if x was both even and odd, then this statement would be true. But this statement's not true, so x can't be both even and odd. You see the logic there?
Mm-hmm.
Alright, let's do another one. If a, have we talked about that symbol?
Yeah, real numbers.
Oh, okay, yeah, just real numbers. If a and b are real numbers, where a is not equal to 0, then ax plus b equal to 0 has at most one solution. There's at most one x I can plug in to make that equation true. So in other words, if 5 happens to make the equation true, when I plug in 5 for x, that happens to make the equation 0, then plugging in 10 for x definitely won't make it 0. It has at most one solution. Does that make sense?
Mm-hmm.
You're used to solving problems like this. Give you a concrete example of one of these. If you see something like 2x minus a is equal to 0, how many x's satisfy this equation?
1.
1.
4.
Definitely not 2 x's that satisfy this equation. Yeah, 4 happens to be the number that satisfies it, but there's only one solution. That's what we're saying. There's at most one solution to the problem.
Just it's not getting include roots.
It's just some number, x, minus some number, equals 0.
But aren't there scenarios where you can have 2x like the negative 2 or 2? Because
When you have a square in there,
yeah.
but no exponent.
So that's the only
Some number, x, minus some number. Only one variable. Okay, everyone feel like they understand what the problem's asking us to prove?
Yeah.
Okay, so once again, assume by way of contradiction that a and b are real numbers and that ax plus b equal to 0 has more than one solution. So we're assuming alpha and not beta. What's the negation of a solution having at most one solution?
Least.
A solution, I'm not sure what I just said. What's the negation of an equation having at most one solution?
That there's more solutions.
An equation having more than one solution, not at most one. Make sense?
Yeah.
So, if it has more than one solution, how many solutions does it for sure have? 2. Maybe 3, maybe 4, maybe 100, but at least 2. If it has more than one solution, it has at least 2 solutions. Because there's no such thing as like a half solution. You can't get in the middle of 1 and 2 solutions. Okay. So, since it has more than one solution, since we're assuming it has more than one solution, then there must exist 2 numbers, call them x sub 1 and x sub 2 in R, such that x1 is a solution. What does it mean for x1 to be a solution? It just means it makes the whole thing equal to 0. And x2 is a solution. It makes the whole thing equal to 0. And x1 and x2 are different numbers. So I'm assuming x1 and x2 are 2 solutions to sync. Everyone follow the logic for number 2? Good? Okay. So then, if ax1 plus b is equal to 0, and ax2 plus b is equal to 0, then those 2 things are equal to each other. Because they're both equal to 0. Right? Subtract b from both sides. Divide both sides by a. Remember, a is not 0, so we can divide both sides by a. And we get x1 is equal to x2.
Or just
x1 is not equal to x2. x1 is equal to x2. So then we have x1 is not equal to x2, and x1 is equal to x2. How possible is it for x1 to not equal x2 and x1 to equal x2? That is as impossible gets. That's our big F. Right?
Yep.
And so there's our contradiction. Therefore, there is at most one solution.
we need to start giving enough.
All right. One more example. 2 consecutive integers cannot both be even. Okay, this one, we first need to figure out what the implication is here. So let's think about that as an if-then statement. Say this to me as an if-then statement.
If there's 2 consecutive integers, then they're not even.
Perfect. If there's 2 consecutive integers, then they're not both even.
Both.
Right? So alpha is 2 consecutive integers. Beta is that they're not both even. Right? What are consecutive integers?
Numbers next to each other.
They're integers right next to each other. 2 and 3, 8 and 9, 26, 27. Those are 2 consecutive integers. So assume by way of contradiction that x is an integer such that x and x plus 1, the 2 consecutive integers, are both even. X and x plus 1, that's what we mean by 2 consecutive integers. Some integer and the one right after. That's 2 consecutive integers. Good?
Yeah, they can't both be.
Well, we got to prove that. You can't say that. Now, since x is even, so I assume that they're both even. Since x is even, then there must exist some integer a such that x is equal to 2a. That's what it means for x to be even. Right? So then, x plus 1 is even. That's what we assumed, that they're both even. X was even and x plus 1 is even. So then x plus 1 is even. And what else is x plus 1? X plus 1 is equal to 2a plus 1.
So it's odd.
So it's odd. So I have x plus 1 is even and x plus 1 is odd. Contradiction. How do I know it's a contradiction?
The last proof.
Because of the last proof. Right here. Here we just barely proved that it's impossible for an integer to be both even and odd. Here I said, therefore this integer is both even and odd. We don't need to redo all the work of our previous proof. You can reference your previous proof. Perfectly fine. Therefore, no 2 consecutive integers can both be even. Make sense? Okay, that's it for new material. Any questions on any of this before we move on to test?
Well, it's pretty easy.
All right. Oh, I forgot to email the test.